Hello and welcome back to Advent of Code 2018, day 22. Almost at Christmas. It's almost over, and then we'll have to begin 2023. Yeah, 2023. So, let's hope this one's not too long. I don't think it will be. It looks like it might be easier than 21. 21 was a bit nasty. So... okay, that is really quiet. What's going on? Ah! There's no audio. There we go. Alright, so, mode maze. It looks like a spatial one with a 2D grid. Good, because I'm good with 2D grids. It's one of my stronger areas. Alright. This is it, your final stop. The year minus 483. It's snowing and dark outside. The only light you can see is coming from a small cottage in the distance. You make your way there and knock on the door. A portly man with a large white beard answers the door and invites you inside. For someone living near the North Pole in minus 483, or I don't know, 483 BC, is that how you say it? He must not get many visitors, but he doesn't act surprised to see you. Instead, he offers you some milk and cookies. Okay. Who is this mysterious white-bearded man? After talking for a while, he asks a favor of you. His friend hasn't come back in a few hours, and he's not sure where he is. Scanning the region briefly, you discover one life signal in a cave system nearby. His friend must have taken shelter there. The man asks if you could go there to retrieve his friend. Okay, the cave is divided into square regions which are either rocky, narrow, or wet. Each region occupies exactly one coordinate, X, Y, okay. The scan is not very detailed, it only reveals the depth of the cave system and the coordinates of the target. However, it does not reveal the type of each region. The mouth of the cave is at 0, 0. The man explains that due to the unusual geology in the area, there is a method to determine any region's type based on its erosion level. The erosion level of a region can be determined from its geologic index. The geologic index can be determined using the first rule that applies from the list below. So 0, 0 has an index of 0. The target has an index of 0. So, if the y-coordinate is 0, then the index is the x-coordinate times 16807. If the x is 0, the index is y times 48271. Otherwise, the geologic index is the result of multiplying the erosion levels of the regions at x minus 1y and xy minus 1. Okay. This seems like dynamic programming algorithm then. We use memoization. And a region's erosion level is its geologic index plus the cave system's depth, all modulo 2183. And you get that. And then you mod 3 it. Okay, cool. And that gives you rocky, wet, narrow. Okay, so far not that complicated. Okay. The example. I don't think I need the example. That's Alright, during this same cave system with rocky as dot, wet as equals, and pipe. So for all intents and purposes, it's basically random. This process mod, I assume these are prime numbers, so that's going to make it look like it's random. Alright. 0, x, y... Okay. What do we want here? Before you go in, you should determine the risk level of the area. So that's our target. For the rectangle that has a top left corner, and a bottom right corner of the region containing the target. So this rectangle here, from M to T, add up the risk level of each individual region. 0 for rocky regions, 1 for wet regions, and 2 for narrow regions. Fine. So you just add up the... That's interesting. So what numbers are we dealing with here? That's it? It's in the thousands? So literally just add them up? Use dynamic programming with memorization. You don't even need to use memorization. You can do this in a iterative way, but I'll just use memorization because it's quicker to code. And if it's too slow, we can do it iteratively, but... This looks suspiciously easy. Am I missing something here? Multiplying the erosion levels of the regions. Just 2 subproblems. So the branching factor is 2. It looks suspiciously easy. Alright, well, we might be surprised, I don't know. Okay then. Maybe part 2 is much harder. So... Okay, so we've got... Alright, 22. Alright, we've got our input is... Oh, we don't need to put anything in. Okay, so we don't need an input. We can just say depth equals... So it's 4845. And target 6770. Okay. We don't need to make a grid even. This is just straight up. What else do we need? We need to know the 2 prime numbers, P1 and P2. So, oh no, let's call it. P1 is 16807. P2 equals this. What else? Just set P equals this. This is the erosion level index modulo. And then what else? Okay. Okay, so we want, basically we want a method which we want to know the erosion. So risk level is the sum of the erosion levels. Yeah. Sum of erosion levels. Get erosion level for X and Y. So we're going to need a table here just to store. Alright, so the rules. If X is 0, return... What was it? So if X is 0, then you return Y... Okay, if Y is 0, return X times... 16807, which is P1. Alright, P1. If X is 0, return Y times P2. If XY in table, so we've seen it before, then return table XY. Otherwise, result equals, so it's going to be, so we take erosion level subsystems depth or modulo 20. Okay, so we take the erosion level, so it's going to be X minus 1 Y multiplied by the same one for X Y minus 1, then that gives us the geologic index. Then we have to add the depth, and so we do that plus the depth, and then the whole thing modulo P. Okay, that gives us erosion level. Do we need to mod 3? No. We could, but we don't need to. Okay. Alright, then finally... table X, Y equals result, return result. Alright, so that's recursive. We're gonna hit the recursion limit, aren't we? We'll see if we hit it. Probably will. Okay, so target T equals 6770, so it's coordinates of the target. Oh, so it's double coordinates, so it's going to be target, target. Okay. So we want... Or we can just do it like this. Let's say total equals 0. So for x in range target or so, but we want to include the value of target itself. For y in range target plus 1 total plus equal, so it's going to be get erosion level, and because I'm doing this from increasing x and increasing y, that means we're not gonna recurse too much. We might recurse in the about 1,000, but not much more than that. So get erosion level. No, we won't recurse at all because we're going from left to right, up to down. Okay, so y and that modulo 3. And then print total. Alright, so far this it seems really easy. Should we just run it and see if it works? It's taking a while. So the target is... Oh, so it's going to be like 100 million, isn't it? But still, that's fine. It might take a while, but it's not going to take too long. So, just wait for it to finish. Is there any faster way? That's probably the part 2. So we're waiting for... So it was 7,000 times 7,000 is, what, 49 million? Waiting for 49 million steps. It's quite a lot, but it's gonna finish within a couple of minutes, I think. Uh-oh. Stop. It's using too much RAM, I think. Maybe I've hit a loop. Stop. What happened there? For X in range target, for Y in range target, total plus equal, get erosion level. Am I definitely not stuck in an infinite loop? We don't actually need to store 100 million steps, do we? We can actually do this iteratively, so we can say what's the clean way of doing this? Do this row by row. Wait, what was the speed of this? Let's have a look. No, not 1,000. Okay, yeah, 1,000. Let's see if it gets to x equals 1 in 1,000. Okay, so it did all the x equals 1000. X percent 1000 equals 0 and y percent 1000 0. Let's have a look. So when we get to there, we're stuck. It's hit an infinite loop. No, it hasn't. What? Okay. $3,000. So this should run. It shouldn't take too long. And 4,000. But why does it stop? Why is there a gap here? Why is it now waiting? It's weird. It should be steady. Oh no, sorry. It shouldn't be steady. That's for x. Fixed value of x. It's doing all the y's and then the next value of x. Okay, that makes sense. Should be done now. What's happened? What's going on? There we go, it's finished. Why is the program not stopped? Okay, just stop it manually then. Strange behavior, I don't know. Too high. Fine, let's test it on the input. So the input, the example is 510. Okay, so depth equals 510, target equals 10. $139? Wrong. It should be 114. Oh wait. The target must have a geologic index of 0. That's forced. Let me change that. So I'm probably using the wrong geologic index. Oh! My calculation's wrong, actually. Okay. Slightly wrong. A couple of things are wrong here. So first of all, I'm mixing up erosion level and geologic index, so don't return here. So geologic index equals that. So before we do anything, we can check if it's in the table. Do that. If y is 0, geologic index that. L if x is 0, it's that. L if x is target and y is target. This is 0. Else it's, so we need to do the erosion level of these. Alright, so now we've got a geologic index. Result is that plus depth. So before I was ignoring this line for these cases. I was just returning 0, so I got the wrong values basically. So now try running it. 114, that's correct. Okay. So I now go back. Yeah, I should get the right answer, but it'll take the same amount of time. Try running it. I think the reason we're using so much time is because we're maintaining a hash table with millions of values. Realistically, we don't need to store all those values. We can only store one row at a time. And then discard. So you basically just need old row and new row. And then when we move to a new row, we flip them. So we discard the old one, the new one becomes the older one, and so on. Okay. For now, it's fine. It just uses a lot of RAM. And hopefully I don't crash the stream. As soon as I see the answer, I can stop it. I don't know why it's carrying on, why the program's carrying on after this print statement. Maybe its cleanup is taking a long time because it's discarding hundreds of millions of things. Alright. Yes, it's pretty bad memory consumption. Uh-oh, stream is crashing a bit. Get ready to stop. There we go. Or, well, that's roughly the same, isn't it? I don't know. Okay. Not the right answer, what? Zero for rock, 1 for wet, 2 for narrow. So it worked for the example. Why did it not work for... Depth is 4845. Target is 6770. Oh, God. That is so confusing. No, that is... Okay, so... Look at this. Nah, that's I thought that was 6,770. So it's going to be 6,770, 6,770. That's actually the X and Y values. That should have been made clearer. That's very ambiguous. Because that does really look like one number. But to be fair, you don't normally put commas in integers if you're expecting them to be parsable, so maybe it was my mistake. Yeah. But still, it was plausible. Okay, fine. Target is 6770. Alright, fine. But it still was a bit ambiguous. Alright, so it's tx equals 6. So we won't use anywhere near as much memory this time. So let's just put this in just for completeness. Alright, so tx, ty, so we want tx plus 1, ty plus 1. So this will be very fast now. Target. If y is 0, x is 0. If x equals tx and y equals ty. Five 400. It was instant. Wow. There we go. Let's check if it's right. Correct. Okay. Okay, it's time to go rescue the man's friend. As you leave, he hands you some tools, a torch, and some climbing gear. Oh my god, this is a long part too. Okay. Hello, Evo dev team. So basically I did about 100 million more operations than I needed to do. So we've got torch and climbing gear. You can't equip both tools at once, but you can choose to use neither. Tools can only be used in certain regions. In rocky regions, you can use the climbing gear or the torch. You cannot use neither. Okay. In wet regions, you can use the climbing gear or neither. You cannot use the torch. Okay, in narrow you can use the torch or neither. Alright, fine. So, in rocky you can use... You must use... either the climbing gear or the torch. In wet you can use the climbing gear, and in narrow you can use the torch. Okay, got it. You start at 0, 0 with the torch. What do they mean by equipped? Okay, fine, it's equipped. And must reach the target coordinates as quickly as possible. The regions with negative X or Y are solid rock and cannot be traversed. The fastest route might involve entering regions beyond the X or Y coordinate of the target. You can move up, down, left, or right if your currently equipped tool allows you to enter that region. Moving to an adjacent region takes 1 minute. You can change what equipped tool you have or put both away if your new equipment would be valid for your current region. Switching to using climbing gear, torch, or neither always takes 7 minutes, so you kind of really don't want to switch if you can help it. Interesting. So each turn you can either move up, down, left, or right, or you can change gear. Fine. Once you reach the target, you need the torch equipped before you can find him in the dark. The target is always in a rocky region. So if you arrive there with climbing gear, you'll need to spend 7 minutes to switch to your torch. So the goal state is to be standing in the final target with your torch out. Okay. Okay, fine. So we no longer care about risk level, but we do care about erosion level, but we've stored that in our table. So in the example, you could... This is just breadth first search then? Not breadth first search, Dijkstra. Because there's varying amounts of time. Moving takes 1 minute. Switching tools takes 7 minutes. So we need to do Dijkstra. So we need a priority queue. So we've got to get to the target in the fewest number of minutes. I don't see any difficulty here. It's just standard Dijkstra. Just make sure we code it correctly. Nice. Alright, fine. Okay, so we do part 1, and that populates our table, so we now have the erosion level for all of those. So this is part 1. Part 2. Let's just, for convenience, let's just create a hang on, let me look at the rules again. Rocky, wet, narrow, 0, 1, 2. Okay. Okay. Fine. So part 2, so we want to do Dijkstra. So start equals 0, 0, that's where we start. But we need a state. So we need 3 parameters. We need an X value, a Y value, and an equipment. So the equipment is torch. So let's say equip equals... So should we say 0 for neither, 1 for torch? Two for climbing. Start X, start Y equals 0, 0. So the starting state is, let's say, the X, the Y, and the equipment. There's nothing else you need to know, right? Okay. We need the notion of distance. So the distance from to the start state is 0. Okay. What else? We don't need a came from. We don't need to remember the path we followed. We just need the shortest path, so that saves us backtracking time. So we don't need the came from data structure. Fewest number of minutes you can take to reach the target. Okay. And then the most important thing is the queue. Priority queue, okay. So we want to put start state. And so the priority is going to be the total amount of time we've taken to get here. So starts off with 0. Wait, no. Oh no, you don't put the priority separately. Hang on, let me look this up again. You have to put it in a tuple, don't you? In which case, oh, so unless you make your own wrapper for prioritized item, then you can separate out the priority, but otherwise it just goes by the value of your item. Fine. I won't bother making my own wrapper. Let's just say we do this. So it'll be dist start state start state. Okay. While not queue.empty. So current time, current state equals queue.get. So we pull out the next state to expand on, which is always going to be the shortest distance. Let's say dist. I know it's time, but I prefer to think of these things in terms of distance. It's equivalent. So current dist, current state equals queue.get. So what do? First, we want to check if we're at the goal, because then we're done. If so, say goal, so goal state equals, so it's going to be tx ty, and the equipment has to be torch. Does it? Let me look this up again. Yeah. Goal state is txty1. Alright, so if current state is goal state print goal reached in time current dist and break out of the loop. Alright, so that's if we reach the goal. Alright, Alright, now what? Now we need to do the bulk of the neighbor method, so, okay, so we don't delete from the queue, so sometimes we're going to put a better path in. So let's say there's some node, some location Z, and at some point we put that into the queue, because we've found a path of 100 to get to it. Later on, we might find a better path, 90 to Z. So we put that into the queue. But the old thing with 100 is still in the queue, and we don't know how to retrieve it from the queue. So at some point it's going to come up, even though we found a better path. So we want to say if current state, oops, if dist, so current state is going to be in dist, but if dist has now got a better distance than what we're looking at here, strictly better, then we have to skip this node. This is lazy deletion, because you can't easily delete things from a priority queue without going through the whole queue, finding it, deleting it off the array, then shifting all the memory and stuff. It's an expensive operation, so yeah, that's lazy deletion. Okay, so now we're guaranteed we're sitting on a state which we found the shortest path to. So we want to lock that in. So, ooh, and this goal state has to come after this, because we might find worse paths to the goal. We need to find the best path to the goal, so that's very important. That has to go second. All right, okay, good. So far, so good. What else? So we could make this an A-star algorithm, but I don't think I need to bother. I think it'll be fast enough. All right, so now we have to do neighbors. So for delta in, so it's going to be 1, 0. So we can go right, left, well, I shouldn't be thinking in terms of right and left, really. Just x and y values. So increase x, decrease x, y. Okay. Okay, for each of those deltas, neighbor x, neighbor y equals alright. Current x, current y, current equip equals, just unpack this state so we've got all the variables we need, equals current x plus delta 0, current y plus delta 1. If neighbor x is gone below 0, or if neighbor y has gone below 0, skip this one. Alright, so, but it's allowed to go as positive as it wants, that's not a problem. Alright, so so this is a valid location, I guess. Anything positive is a non-negative is a valid location. What else? Now we need to do the equipment check. So the rule was we can only enter a new spot if we have the right tool for the area. So let's see. If okay, neighbor type equals get erosion level neighbor X neighbor Y %3. If neighbor type is 0, so that's rocky. Okay, so if it's rocky, we're not allowed to have no equipment, basically. So and and current equip. Oh, there's one more state. Oh no, we can deal with that later. Okay. So 4 movements. Okay. And then we'll deal with changing equipment. So 4 movements are each, there's 4 different potential neighbors. So if neighbor type and current equip is 0, that's invalid. So skip this one. If neighbor type is 1, and so if it's 1, it's wet. So we're not allowed to use the torch. Continue. If neighbor type is 2 and current, so this is narrow, so we can't use the climbing gear. Ah, so this is nice. It basically, if type matches current equip, we can just do that. It just works out. I guess they did that on purpose. Alright. So neighbor type is not allowed to match the current equipment. The integer. Okay, fine. Alright, so now we know this is a valid location, so neighbor dist equals current dist plus 1. That it's 1 minute, right? Was it? 1 minute, yeah. Okay. If so neighbor state equals, so now we've got our neighbor state. It's going to be neighbor X, neighbor Y, and then current equip. If dist, if neighbor state in dist, so we've already found that state before, and what we found before was better. Strictly better, then we skip this neighbor because it's just not better than what we found before. Alright, if we got this far without hitting any of these continues, that means we've found a better path to the neighbor. So we're going to put that in the queue. So we want to say dist neighbor state equals neighbor dist q dot put, so it's going to be neighbor dist neighbor state. All right, and then to equip changes, we can change the equipment twice. So for neighbor equip in 0, 1, 2, if neighbor equip is the same as what we currently have, skip that one. Alright, so otherwise, this is valid. We're allowed to change to those other... Oh, wait! You can change your currently equipped tool or put both away if your new equipment would be valid for your current region. Okay, fine. So you got to check that it's valid. So we... so we want to check... this. Current type equals get erosion level current X current Y SM3. If neighbor equip equals current type, that's bad. We can't change to that. Continue. Hang on. I haven't, we're gonna duplicate code here. Oh, whatever. It's not a big deal. We can duplicate code. Alright. I should have done this. I should have made a list of neighbors and then... it doesn't matter. Okay, so, so... in this case, neighbor state is gonna be where we're currently standing. So it's gonna be current X, current Y, the new equipment, neighbor dist equals current dist plus, was it 7? 7 minutes, okay. And we just have to duplicate this code. I don't like to do this, but just cut corners here. So if it's in dist and we've found a faster path to this state before, we'll skip it. Dist. The distance is now that neighbor distance. Queued up put neighbor distance neighbor state. Got it. Anything left to do? That's quite a... it's quite a mouthful, but... think we're done. Should I just run it then? So we've got... So, in the worst case, it's going to try... In every location we can enter, we can have... So there's like 10 times, let's say like 10,000 locations in this rectangle. You can go outside the rectangle though, but roughly we're going to go to 10,000 different locations. For each location, you can have 2 different equipments. So, maybe in the tens of thousands. Okay, it should be quick. Let's run it then. Well, it is going to branch a bit, but it's Dijkstra, so it should be reasonably efficient. But it expands in its breadth, so we're basically going to be finding the shortest path to all like the all of the locations in a kind of circular pattern emanating from our origin until we hit the target. So we are going to cover a lot of locations. But I mean, it shouldn't be in the tens of millions or anything, because we never put a neighbor in unless it's the best path we found to that neighbor, and that's not going to happen too often. We don't just keep visiting neighbors over and over again. It is taking a while though. I could make this an A-star algorithm. What is the minimum amount of time you'd spend to get somewhere? It would just be the X and Y coordinates. 1 minute for the horizontals, 1 minute for the verticals. So it'll just be the Manhattan distance, wouldn't it? This is taking too long. Might need to convert it to A-star. Ah! No, that's fine, that's fine. Should we switch to A-star? Yeah, this is a bit slow. Let's try and speed this up a bit. Alright, so I want to see, just have a rough idea of how am I going to do this? Oh no, I'll switch to A-star first. Fine. So the heuristic given state is an estimation of how long it'll take to reach the goal. Minimum amount of time. So the most obvious thing to do is just the sum of x values and sum of y values. So it'll be so x, y. We don't care about the equipment. Actually, we do. We probably have to add 7 if we don't currently have the equipment. Okay. Quit. So so we basically want to return. So it's the absolute value of tx minus x. So that's how many horizontal moves we need to do, plus the absolute value of ty minus y, the number of vertical moves we need to do, and then 7 if we're not currently carrying a torch. Because no matter what, if you're not carrying a torch, no matter what, you need to, at some point, spend 7 minutes to switch. So that's an important thing to include. That'll prioritize keeping a torch ready when you're near the goal. Okay, so that's the heuristic. That's a pretty good heuristic, I think. And good means close to the actual amount of time, but it's not going to be because we're going to have to spend a lot of time with changing equipment and stuff. But whatever, it's all right. So queued output. So it's going to be. So that's the heuristic, so we want to put the distance of the start state, which is 0, plus the heuristic of the start state. The estimated amount of time it'll take to get to the end. This current dist here is useless now. Let's get rid of that. So now we need to know what the current distance is. Let me have a look at the Wikipedia for this. I forget what the best structure is for this A-star algorithm. I think we need another day to keep track of the... I think what we're doing is fine, but we might... Okay, I think what we're doing is fine. Just carry on. So... current dist equals... This is the best known... This is the shortest path to this node. Except... later on we're gonna get this node appearing again. So that will waste some time, but that's not a big deal. Whatever. Okay, so... So, that's our state. That's the current distance. If we've reached the goal, yeah, that's fine. And now we just do everything as normal. Until we get to this bit. And now we need to add h of neighbor state, the estimated time to get to the end. Similarly here. So this is why you shouldn't duplicate code, because now I have to make these changes twice and make sure not to forget them. So that's everything, right? That's what it takes to add a heuristic. So this should be faster, hopefully, because now it's going to prioritize a sort of diagonal path towards the goal instead of expanding laterally. Let's try it then. So if this doesn't finish within the next few minutes, then I might need to print some logging and see if I'm stuck in a loop or something. Also, stop. So if we've already found... So this should be greater, less, or equal to. That's saying if we found a path to this neighbor state before with the same distance we've already found here, then that's also pointless. We don't need to redo that neighbor. So let's change these to less than or equal to. That's going to make a big difference because I've got duplicates now. Because of the lazy deletion, sometimes we're going to come across nodes that we've already dealt with before. Okay, change that. Alright, just run it again then. Alright, let's just see what happens. Oh, and that was quick. That change made all the difference. Because I was just going around in circles, repeating called neighbors. Goal reached in time 1048? Does that sound about right? So it's roughly... So the shortest path, if you're not worried about changing equipment, is going to be about... Well, it's going to be 776, exactly. That's how many moves it takes. And then you're going to have to add a bunch of 7s for... the tool switches, but also the path is probably not going to be linear. Sometimes you might find some faster routes. So, that sounds about right. Correct? That was a nice problem, but it was pretty textbooky. There was nothing too... I think part 1 was actually the more interesting one. Well... Okay, part 2 was technically harder, but if you know A-star, then you kind of know what to do. It's textbooky, but part 1 was the one where you had to think a bit more carefully, I think, because then again, I did kind of mess that up. It would have been much easier if I just used the correct input. They were fairly generous because you could have gone with much bigger numbers here, and then you'd have to use a row-by-row approach instead of storing the whole 2D grid in memory. So that was 22. Yeah, this was an easier problem. I think a lot of people did get stuck on part 2. Maybe they don't really know how to do A-star, or they did breadth first search. A lot of people don't do A-star, they just do breadth first search. Sometimes it's not enough. Most of the time it is enough, though. But sometimes it's not enough. And then the best approach really is to expand to A-star, but sometimes people just spend a lot of time trying to find micro-optimizations, which might help, but I think just go for A-star. Some people are scared of A-star because it seems complicated, but it didn't take me that much longer to add in the H function, so... I think that's the best H function you can do. I can't think of anything better than that, because that's the minimum amount of time you need, right? Yeah, I don't think there's anything better than what I did for the H function. Because I could draw a map which takes exactly that amount of time, where everything is rocky, let's say, and you got your torch equipped, or not equipped, and then you can just walk to the goal and change your torch, but... So that is actually the optimal heuristic. Alright, well, that took 1 hour, 20 minutes, roughly. So I've got 3 problems left, and like 4 days left. That's... I might not always have time to do a stream each day though, so I'm debating whether to move on to the next problem now, but that might take me another 2 hours. We'll go for another problem tomorrow. Okay, so Amaro said that 23 is apparently the most controversial problem. We could take a sneak peek. Apparently it's the most controversial problem of this year. So we're working with 3D coordinates, the radius, which is using Manhattan distance, so that's a nice clean distance to use. It's not like Euclidean or anything. No floating point operations. It looks like you're computing the weight of disks of radius r using Manhattan distance, so actually squares, the weight of squares by summing all the elements of that square. It looks like that's roughly what this is. Oh, I see. This is a geometry problem. Something like that. We'll find out tomorrow. Oh, and these are big numbers. And these are... Whoa, these are big radii, so yeah. I think a lot of people went for the brute force approach. I think you're going to have to do some geometrical trickery. Like when you have a square overlapping another square, the overlapping bit is then going to be a rectangle, so you have to think in terms of rectangles. Right, well, we'll do this tomorrow then. We're not gonna get a break, are we? As soon as I finish this, I'm gonna have to do the actual 2023 one. Maybe I can try and cram in 2 problems tomorrow. Oh yeah, Amaro's joined the leaderboard. So yeah, if anyone watching wants to be on this leaderboard, so we can like just as a friendly thing, just see who's completed what problem, then you just want to use that code there. It will also be in my YouTube description when I upload this to YouTube later. Oh no, this is an old leaderboard, we don't care about that. In fact, should I just leave it? It's whatever, we can stay on that leaderboard. Okay, so that was a nice textbooky, very textbooky. I don't think there was anything we had to do creative there. That was a standard textbook problem I would give in a standard 101 algorithms course in a university level computer science. That standard Dijkstra. I mean, I studied Dijkstra in school, so it's. But this is a bit more complicated than the type of Dijkstra I did when I was in school. Standard Dijkstra, standard dynamic programming with the memorization. But you need to know that stuff, so it's good to practice it. And I always try to write my Dijkstra algorithms from scratch instead of... I could just make a text file somewhere where I've stored it, so I just paste it in every time. But I always write it from scratch. It just helps hammer in the point of all those data structures and why you do this and why you do this in a certain order and stuff like this. Yep, so now because I finished reasonably early compared to some last streams, I could actually go play some, I don't know, Super Mario RPG or something. I think I want to play that. Okay. Alright. Thank you for watching. See you probably tomorrow. Unless I'm like hungover or something comes up, I don't know. Bye-bye.